Chapter 9 talks about electrons and atoms and the periodic table. The whole point of chapter 9 is to explain where the electrons reside in the atoms. Chapter 9 is more of a theoretical chapter. There's not any calculations in chapter 9. Remember that when we first talked about the periodic table and the atom back in chapter 4, we described the atom as having a dense nucleus. And we said inside that nucleus, we had the protons and the neutrons. The protons carried a positive charge. And I said, like, if I were to draw an atom, so this is my dense core right here with protons and the neutrons in it, then we had these negatively charged electrons floating around the positive nucleus. Do you guys remember this?
Yes.
Yes.
Okay, so now this isn't actually how the electrons reside in the atom. It's really complicated. It goes all the way up to quantum physics, talking about where electrons reside in the atom. And we're just gonna kind of get a basic understanding of how the electrons reside in the atom. We're gonna figure out what is known as the electron configuration, which is just saying where the electrons would reside, what shells, what levels they would be in the atom. And we're not going to get so deep into it because it gets really deep. It involves calculus and wavelengths and things like that. But we're just going to get a basic understanding of how the electron resides in the atom. Now, it's really complicated. The electrons pretty much make up a lot of things that exist in our world and how they work. It's really fascinating to me. I did a lot of my thesis research on light and what we're going to talk about in this chapter. So I do think it's fascinating, but it can get a little confusing, and I'll try to break it down as simply as possible. So the two models that we're going to talk about in this chapter are the quantum mechanical model and we're also going to talk about the Bohr model. And I'm going to briefly talk about both of these, but the main focus of this chapter is trying to figure out the electron configuration. And both the quantum mechanical model and the Bohr model are just models. I'll say they're just models that explain the behavior of electrons as they exist within the atom. So if we just remember, that's the whole point of this chapter. We're just trying to explain the behavior of electrons as they exist. The electron configuration just gives us a layout or a scheme of how the electrons exist. But before we get into too much detail about that, we first have to talk about light, which is considered electromagnetic radiation. All right, so this is light. And all electromagnetic radiation is, when I say light, I literally mean like the light that's shining in your house right now, the sunlight, all the light that we see around us. All electromagnetic radiation is, in reality, is a type of energy that travels through space at a constant speed of 3.0 times 10 to the power of 8 meters per second. And we call this the speed of light. Another way we can say it is 186,000 miles per second.
I'm sorry, is that a -8 or is it just 8?
It's a regular 8.
Oh, it's a regular 8. Okay.
Yeah, no negative. It's a positive 8 is what I mean to say. So basically it's saying 3.0 times 10 to the power of 8, which is like, what's that? 300 million meters per second. And that's the speed of light. So let me just write that here, speed of light. All right, so when we talk about light, we can characterize light by two different things. One is its wavelength. And the wavelength, it's given by the symbol lambda, which kind of looks like an upside down Y. And all the wavelength is, it's just kind of what it sounds like, the length of a wave. If we think of light as a wave, just like a wave in the water. We think of a wave like this. The wavelength is basically the length between each peak, or we could say the length between each trough or a crest. So this is considered the wavelength from peak to peak. On the other hand, we can also characterize light by its frequency. And frequency is basically, it's characterized by the Greek letter nu, which looks like a V. And it's just a number of cycles or peaks that pass through a stationary point at 1 second in 1 second. So let's say I have a wavelength that looks more like this. If we compare these two wavelengths, this wavelength would say that it has a higher frequency because basically it has more peaks per second or more cycles per second. So it's basically cycles per second. And we'd say that this has a higher frequency than this wavelength over here. So from these two pictures, we can see that frequency and wavelength are inversely related, meaning as the frequency increases, you see as the cycles increase, that means that the peaks are closer together, and that means that the wavelength, the distance between each peak, is shorter. So as one increases, the other one decreases. So I would say that they are inversely related. I'll just put a little star here saying frequency and wavelength are inversely related. Meaning as one goes up, the other goes down. All right, so scientists in general used to think that light could only be characterized by waves, but then Albert Einstein came along and said some properties of light can only be explained by particles. And so it's basically saying that a particle of light or light can also work in a stream of particles, and that stream of particles we call a photon. So what I'm saying now is that light has wave-like properties and particle-like properties. So we just say a photon is a particle of light. And we can think of it as a packet of light energy. Yeah, that's fine. Now, the amount of energy carried in each packet of light, the amount of energy carried in each packet is related to the wavelength. So I'll say that too. And each packet of light depends on the wavelength. So basically, the shorter the wavelength, the greater the energy. I dropped my paper. So the shorter the wavelength, just like with frequency, the shorter the wavelength, so longer wavelength versus shorter wavelengths. This is a longer wavelength, which means less frequency, which also means less energy. Where on the other hand, when you have a shorter wavelength, you have higher frequency and higher energy. So energy and frequency are both inversely related to wavelength. So the electromagnetic radiation, it ranges. And we have what is known as the electromagnetic spectrum. And on the electromagnetic spectrum, it's a big range of energy, and the light that we see, the visible light that we see, is just a very small, tiny portion of the electromagnetic spectrum. So let me show you in the book. If we look in the book, here on this image in the book, we have what is known as the electromagnetic spectrum, which ranges from 10 to the power of 6 or so, all the way to 10 to the negative 16th. And that's the amount of energy. But then when we talk about the wavelength, we see the higher the energy at 10 to the power of 5, the longer the wavelength is. And then when you get to having less energy, the wavelengths and the peaks get closer together. This small little portion right here is the only portion of the electromagnetic spectrum that we can see. This is called the visible light, and it ranges from red, which red would have the longest wavelength, to blue/violet, which has the shortest wavelength but the highest amount of energy. So I'm just gonna list these out really quickly for you guys, just to let you know the different types of electromagnetic radiation there are, and then I'll keep going.
I mean, that's in the book, right?
Yeah, that's in the book. That's on page 288, and you can also just Google electromagnetic spectrum, and that same picture will come up.
Okay.
Electromagnetic spectrum, or a similar picture will come up. All right, so on the electromagnetic spectrum, we're gonna start off with gamma rays. Gamma rays have the highest energy. So I'll say highest energy / frequency. When we talk about gamma rays are the rays that are produced by the sun and other stars. They're unstable. They have unstable nuclei, and they destroy biological molecules. So gamma rays are very dangerous to us. We shouldn't come into contact with gamma rays, and so they basically can kill us at the end of the day. All right, so gamma rays have the highest energy and frequency, which in turn means they have the shortest wavelengths.
I'm sorry, Professor.
Mhm.
You said that it's produced by the sun and what else?
And stars, like
Sun,
the sun and other stars. You know, like the sun is just a star in our
Right.
solar
Okay.
system. It's saying just other stars produce gamma rays.
Okay. Thank you.
All right, next on the spectrum is, and I'm going in order from highest energy to lowest energy. So next on the spectrum is X-rays. And X-rays, many of us have probably had an X-ray taken before. If you've gone to the dentist's office, they've X-rayed your teeth, or maybe even if you've gone to the hospital, you've had other X-rays taken. X-rays are dangerous for us too. They damage internal organs and bones. And they just know when you go to take an X-ray, think about going to the dentist, they always make you wear like a lead vest to protect you from the X-rays. They only want to get your mouth. They don't want to touch your internal organs or anything like that. Next on the electromagnetic spectrum is ultraviolet light. / UV light. Many of us have heard of ultraviolet light or UV light. It's basically produced by the sun. It's how we get our suntans and our sunburns. So ultraviolet light can cause cancer. It's not good for us to be exposed to a lot of UV light. And that's why we're always told to wear sunblock when we go outside and things like that. Then there is visible light. Visible light is the only portion of the electromagnetic spectrum that we can see. And so the visible light, it ranges with highest frequency being blue to orange. I'm sorry, not orange, red. So I'll say high energy / frequency to lower energy / frequency.
So for this, blue is considered high, correct? And then
Yep.
red. Oh,
So think of like, what is it? The rainbow colors are Roy G. Biv, red, orange, yellow, blue. I don't remember them. Roy
Yes.
G. Biv. You know what I'm saying? Red, orange, yellow, green, blue, indigo, red. So if you red, orange, and yellow are going to have lower frequency than the group green, blue, and indigo. Do you get what I'm saying? That indigo goes into the UV light, which is kind of like ultraviolet, like a purple.
Okay, ultraviolet. Okay.
Yeah. All right. So then if I keep going, the fifth one is infrared light. And that is considered IR. Some of you guys might have heard of IR. IR is technically heat that we can feel when we place our hand near a hot object. All warm body animals emit IR. So we emit IR, you know, sometimes you guys have seen like night vision cameras, whether you've seen it in person or on movies or something like that. The night vision cameras uses IR technology to where warm body animals will glow red or orange on the screen when you use the night vision cameras. So they're just using the heat that's emitted from all warm body animals. All right, so then next there is microwaves. And microwaves, they're used for radar, microwave ovens, you know, they have a distinct property to be able to rearrange water molecules. And so, you know, think about putting your food in the microwave. If there's no water in your food when you put it in the microwave, it heats up like all burnt like. So you always want to add some water to it or put like a wet paper towel over it. So that way your food in the microwave will heat up properly. And then the last one is radio waves. And radio waves transmit signals used by like AM and FM radio. So AM, so I said AF, AM and FM radio. AM stands for amplitude modulated and FM stands for frequency modulated. So one tunes the frequency, the other one tunes the amplitude. And basically all the technology like our cell phones and the internet and all that stuff works off of radio waves. And this radio waves, I'll say cell phones, internet, all the technology we're using works off of radio waves, and it's mainly because they have the lowest energy / frequency. So their energy does not harm us. All right, so questions that you guys would see in regards to the electromagnetic spectrum would be, let's say, for example, the question would say, arrange these three types of electromagnetic radiation in order of increasing just in order of increasing. How about that? Let's just stop there. So let's say we have visible light, we have X-rays, and we have microwaves. And I want to arrange them in order of increasing A, which would be wavelength. And I want to arrange them in order of B, which is, let's say, energy. Now, do we understand what increasing means? Increasing means we're going to go from smallest to largest. We're going to increase. So I would put those three types of electromagnetic radiation in order from smallest wavelength to largest wavelength, and then in order from lowest amount of energy to highest amount of energy. So let's spend a second and see if you guys can get that together.
You said lowest to highest, right?
Yep, increasing means lowest to highest. Yeah. Right, what do you guys think for wavelength? Which one has the lowest wave or the shortest wavelength? What would you guys think out of these three?
Microwave. I think that's what
Microwave?
Microwaves, you're saying has the lowest wavelength?
Visual lights.
X-rays.
Microwaves?
It's X-rays.
X-rays.
Yeah, so when we think about the spectrum, remember, we're gonna go in order. If we say, remember gamma rays is number one, it has the highest energy / frequency, but the shortest wavelength. And then we go all the way down to number 7, which is radio waves, which has the lowest energy, but also has the longest wavelength. So this question's saying which one of these has the shortest wavelength and then increases to the longest wavelength. So if I look on the order from 1 to 7, we'd say X-rays.
So it's basically opposite, right? So the lowest, the higher energy, and then from like.
Yeah, exactly.
Yeah, okay, I see.
Yeah, I just want you guys to see the relationship. They're going to be opposite from each other. So if the wavelength is shorter, that means it has a higher energy. So what comes after X-rays? Is it going to be microwave or visible light?
Visible?
Visible light. And then we'd say, what was it, microwaves? Microwaves. But then when we look at it in terms of energy, if you want to know which one has the lowest energy, it's the opposite. Like Sandra said, it's going to be microwaves, visible light still in the middle, and then X-rays. So basically, that's what you guys would have to know from this information. Just like the order, you'd have to know that blue has higher energy than red light, or that red has a longer wavelength than blue light. You know, so those are the things, those are the types of questions you guys would be asked from this what I just told you. All right, but so before I keep going, do I have any questions?
No.
All right, and to sum this up, just know that wavelength and energy, or wavelength and frequency, are inversely related to one another. And that even though we call light, we call it light, it's really called electromagnetic radiation. It's a type of energy. We don't consider it matter. Remember, matter has to have mass and occupy space. And we call this energy, and there's different types of electromagnetic radiation. And these are the 7 different types. The only part that we can see is the visible light. So all the rest of this energy is floating around us. We just can't see it or feel it, okay? But it's still there. I think energy is kind of like, and you can do a lot of things with it. All right, so if I keep going, and we relate this to the periodic table, or just elements and atoms in general, what ends up happening is that when an atom absorbs energy, or any type of energy in the form of heat, light, or electricity, it often re-emits that energy as light. And we call this emission. When an atom absorbs energy, whether they absorb that energy as heat, light, or electricity. It often re-emits that light re-emits that energy or light, or just that energy as light. So the book gives an example for, I'll say example, if we think about neon, we've seen neon signs. Neon's an element on the periodic table. All a neon sign is a glass tube that's full of neon gas. And that neon gas, when an electrical current passes through it, the neon atoms absorb some of the electrical energy and re-emit it as red light. So neon gives off red light, is what I'm saying. Other atoms, for example, the book gives an example of mercury. If I have a mercury lamp, mercury is going to give off blue light. And then hydrogen gives off kind of like a pinkish light. And that's basically, if I have these lamps set up that are full, like a glass tube of neon, a glass tube of mercury, a glass tube of hydrogen. If you guys have heard of halogen lamps are just lamps that are filled with halogen gas. And we know what the halogens are. They're elements in group 7. So it's just saying when you mix these gases together, they give off certain colors of light. And this is true for most atoms or most elements on the periodic table. And, you know, scientists were perplexed back in the day, like, why does this happen? We don't understand why this happens. So a simple model to explain why this happens came about, which is known as the Bohr model. And I'll talk about the Bohr model.